Welcome back to the deep dive. Today we're taking a whole stack of your sources. We've got articles, design patterns, research notes, and we are finding those essential nuggets you need to get fluent fast.
And today, we're diving into what is, well, you could argue it's the programmer's greatest challenge.
Ugh.
How do you deal with objects and functions that are really similar?
Right, and how to avoid duplicate code. I think every source you sent us used the word evil to describe it.
They did, and for good reason.
Yeah.
It just makes debugging an absolute nightmare, and, maintaining the code becomes almost impossible over time.
Exactly. So our mission for this deep dive is to give you a definitive shortcut. We're going to unpack the main techniques for this, focusing on the strict rules of inheritance and then the incredible flexibility you get from mix-ins and duck typing.
We're really looking at the core design patterns that shape how objects talk to each other and share behavior. Getting these distinctions right is, it's the difference between code that just works and code that's clean, scalable, and genuinely object-oriented.
Okay, let's unpack this. We should probably start at the very foundation of similarity.
The first concept, the one we all learn in Ode 101, is inheritance.
And when you use inheritance, you're basically establishing an is-a relationship. You're saying one thing is a type of another thing.
That's the starting point. You have a superclass, you'll hear it called a base class or parent class.
Yeah.
And that holds all the common code, all the shared methods, the attributes, everything.
And then the subclasses, the child classes, they just automatically get all of that. They inherit it.
Exactly. They take that base structure, and then they can either add to it, extend it, or they can change part of it, override it with their own specific details.
It's probably worth mentioning for a second that technically every class you ever create, no matter how simple, is already inheriting from that built-in object class.
Right.
But we're focused on the hierarchies we build on purpose.
And those hierarchies, the ones we design, are governed by a really critical rule that can make or break your entire design. It's called the Liskov substitution principle.
LSP, that sounds formal. Why is it so important?
Well, it's the ultimate test for whether your inheritance structure is sound. It just states that a child class must be able to replace its parent class anywhere in the code, and the program should still work perfectly.
Without causing any errors or weird behavior?
Right. But, and this is the crucial part, the reverse is never allowed. A parent can't just stand in for a child. If you can swap the child for the parent and everything works, your design is solid.
And the sources gave us this fantastic, super simple litmus test for this. It's a two-part check. Let's use the classic example, right? A square and a rectangle.
Perfect.
So first step, you ask if B is an A. So is a square a rectangle? And yeah, structurally it is. It has four sides, four right angles. It fits the definition.
Okay, step one passes. Now step two, you flip it. Is a rectangle a square?
And the answer there is a clear no. A rectangle doesn't have that extra rule that all four sides have to be equal.
So, because you can only justify it one way, B is A, but A is not B, inheritance is the right tool for the job. A circle is a shape, but a shape is not a circle.
But the sources were really clear on this next point. If you find you can justify it both ways, if A is a B and B is an A, then you should never use inheritance between them.
Absolutely not. That's a huge red flag, that you've got two classes that are actually peers. They're not parent and child. They should probably share a different, more abstract parent, or you need a totally different approach.
And that all comes back to LSP, to that idea of predictability.
Yeah.
If I have code that expects rectangle and I drop in your square class and it suddenly breaks my logic.
You violated the principle.
Yeah.
And now you have these incredibly subtle bugs because the behavior wasn't what you expected. The hierarchy wasn't predictable. That's the key word.
Predictability. Got it. So that is a test. Keeps our designs clean. But what if we just want to, add a little extra functionality to something that already exists, like a basic list or a dictionary?
Now you're getting into the real power of inheritance.
Yeah.
It's not just for sharing code. It's for customizing and extending what's already there.
So you can take a built-in class like list or dict and just add to it?
For sure. A great example is a contact list. You can make it inherit from the standard Python list, but then add your own special methods, like a search by name method. Your contact list is still a list. It does everything a list can do, but now it has this extra superpower.
Or for a dictionary. What could you do there?
You could do all sorts of things. You could extend dict to, say, keep track of the longest key it's ever seen, maybe for some kind of optimization. Or, and this is a really practical one, you could change its core behavior so it throws an error if you try to add a duplicate key. instead of just silently overwriting the old one.
Oh, that would save so much debugging time.
Exactly. And this is where it gets really interesting because it's not just about adding new things. It's also about overriding what's already there. We do this all the time with those special methods, the ones with the double underscores.
Like init or star.
Right. You can completely replace their behavior or you can chain them. You can say, okay, first run the parent's init method to do the basic setup and then run my extra code.
Chaining sounds pretty essential. You wouldn't want to accidentally skip the parent's setup.
You definitely don't. The parent might be opening a file or connecting to a database. You need that to happen first.
Okay, this brings us to a concept that is, well, it's a bit tricky. Multiple
This is a
inheritance.
source of much debate.
Right. Where a single child class inherits from more than one parent. I love the saying one of the sources used. If you think you need multiple inheritance, you might be wrong. If you know you need multiple inheritance, you might be right.
It's a great warning. And the reason for all that caution is this one famous problem, the diamond problem.
Can you walk us through that?
Sure. Imagine you have a class, let's call it D, and D inherits from two classes, B and C. But B and C both inherit from the same top-level ancestor, Class A. So you have a diamond shape.
Okay, I can picture that. A at the top, B and C in the middle, and D at the bottom.
Exactly. Now, what happens when you create an object from Class B and you call a method that was originally defined way up in A? Which path does Python take? Does it go through B first or C? And more importantly, how many times does A's initializer, its init method, get called?
Could it get called twice?
It could. Or in a really complex hierarchy, it might not get called at all. And it's incredibly dangerous. If that base class is what sets up a database connection, you've either set it up twice, wasting resources, or
Yeah.
you've skipped it entirely and your object is just broken.
So there had to be a solution for this.
There was. The super function was developed specifically to solve this ambiguity. Instead of you having to manually call parentClass.method, which is messy, super automatically figures out the correct next class in the chain and calls its method. It navigates the diamond for you.
And Python actually shows its work, right? There's a way to see the exact order it's going to use.
Yes, and it's so useful for debugging. You can look at the method resolution order, or MRO, for any class using the marrow attribute. It gives you a tuple that literally shows you the precise order Python will search through the parent classes to find a method. It makes the unpredictable predictable.
Okay, now that we've seen how Python resolves these complex chains, let's connect this back to one of the main reasons we use inheritance to begin with, polymorphism.
Polymorphism really is the end goal of good object-oriented design. It's this powerful idea that different objects can respond to the same message, the same method call, in their own unique ways.
You could have a bunch of different objects, and they all have a save method, but what save actually does is totally different for each one.
Precisely. Think about a media player. It needs to handle WAV files, MP3s, OGGs. They all need different decoding logic.
So instead of having playwav, plamp3, playog,
You just have a single public API, a play method. The code that uses your objects doesn't care what kind of file it is. It just tells the audio file object to play. The specific subclass, whether it's MP3 file or WAV file, knows how to handle the details. That's polymorphism in action.
but Python has its own unique spin on this, which is where things get really flexible. It's called duck typing.
It really is a philosophical shift. Python lives by the duck test.
If it walks like a duck and it quacks like a duck, then it must be a duck.
Exactly. It means Python cares more about what an object does than what it is.
So it doesn't check its family tree, it doesn't care if it inherited from audio file.
Nope. It just looks at the object and asks, does this thing have a play method that I can call? If the answer is yes, it works. It doesn't care about the object's class or its inheritance hierarchy at all.
That seems incredibly powerful. It means you can use any object that has the right behavior without forcing it into a strict class structure.
It's why polymorphism in Python is so much less rigid than in, say, Java or C++ Love. You could have a FLAC file class that has zero relationship to your other audio classes. But as long as it implements that same play interface, your media player code will work with it perfectly. It's behavior-based, not class-based.
That focus on shared behavior over shared ancestry is the perfect transition to our last big pattern, the Mixin.
Mixins are fantastic. They're often called the simplest and most useful form of multiple inheritance.
And the key difference is a Mixin class isn't meant to be used on its own right. You never create an instance of a Mixin.
Never. It's designed specifically to be mixed in to another class just to provide some extra functionality. You'd say a class is using a Mixin. Not that it is a Mixin, it's a different conceptual relationship.
So it's a way to share code without that strict is a bond.
And it completely sidesteps the confusion of the diamond problem, because Mixins are usually very focused. They do one thing well. A great example from the sources was an is dictionary Mixin.
Right, and all it does is provide a single method, todict, that turns an object's properties into a dictionary.
Exactly. Now, you could have an employee class and an address class. They have nothing in common. An employee is not an address. But they both could benefit from being converted to a dictionary.
So they can both just mix in that functionality.
They just inherit from the is dictionary Mixin, and boom, they both get the todic method for free. It's a beautifully clean way to inject behavior across unrelated classes.
But with all this power, inheritance, polymorphism, mixins, there's a pretty big warning label that comes with it.
There is a huge one, and it leads to something called the inheritance tax.
The sources had an amazing quote for this from Joe Armstrong. He said, "You wanted a banana, but what you got was a gorilla holding the banana and the entire jungle."
It's the perfect analogy. It perfectly captures that feeling of being coupled to something you don't control. When a child class inherits from a parent, they are tightly bound together.
Meaning changes in the parent can break the child in unexpected ways.
Or just weigh it down. You only wanted that one useful method, the banana. But to get it, you had to inherit from a massive parent class that brings along all this other baggage you don't need. The gorilla and the jungle. You're paying a complexity tax.
So if is-a can be too restrictive and costly, what are the better alternatives for sharing behavior?
Well, the sources suggest three primary alternatives. First, just use interfaces and protocols. Rely on duck typing to get that polymorphic behavior without the tight coupling of inheritance.
Okay, what's second?
The second is delegation, which is also known as composition. This is all about favoring a has-a relationship over an is-a relationship.
So instead of saying a car is an engine,
You say a car has an engine, the car object holds on to an engine object internally. When the car needs to accelerate, it doesn't do the work itself, it just delegates that task to its engine object. This decouples them completely. You can swap in a different kind of engine without having to change the car class at all.
and the third alternative.
Is using Mixins, just like we discussed. They are the perfect tool for sharing specific pieces of functionality without creating that heavy conceptual is-a bond.
Wow. Okay, that was a really fast but really deep dive. We covered the strict LSP rule for inheritance, untangled multiple inheritance with MRO and super, saw the freedom that duck typing gives you, and then landed on mixins as a smart way to share code while avoiding that inheritance tax.
You now have a really solid framework for thinking about how to structure your objects. But before we wrap up, there was one last really provocative thought in the sources that I think is worth sharing.
Oh yeah, this was fascinating. We saw how object-oriented design can lead to these really elegant solutions for some tough competitive programming problems, things like statistics, datum, or tech.
But here's the twist.
Hmm.
The source specifically warned that for the teak problem, the elegant ode solution might actually be too slow. The overhead that inheritance adds could cause the solution to fail the tests, which have a strict 2-second time limit.
Which leaves us with a really important question for you to think about. When does beautiful design have to take a backseat to raw performance? Is a simpler, maybe less elegant solution sometimes the right call when every millisecond counts?
That tension between design purity and real-world constraints is something every developer has to navigate on their own.
We'll catch you on the next deep dive.